I want to talk about the first of many flow rate problems. This is something that you're very likely to see on the AP exam. What I mean by a rate flow problem is imagine that we have this tank and water is getting pumped into the tank at a rate of W of T equals 95 square root T times sine squared T over 6 gallons per hour. And at the same time, there's water coming out of the tank. So maybe there's a hole in it or there's a spigot or something, but the water is coming out of the tank at a rate of R of T equals 275 sine squared T over 3. This model holds true for all T from 0 to 24 hours. So within one day, these are the rates of flow of water coming in and out of this tank. Now, first of all, at noon, when T is 12, is the tank being emptied or filled? Now, an important thing to remember with these types of problems and these two functions is that these are rate of change functions. So it's like they're already derivative functions. So when we want to see what W is at noon, and we just take 12 and plug it in there, we'll have our 95 square root of 12 times the sine squared of 12 over 6. And we can go ahead, tappy tap that into the calculator. We get 272.098 gallons per hour. So that's the rate, the speed at which the water is getting pumped into the tank. Then we think about the water that's coming out of the tank. And we find R of 12. So that'll be our 275 times the sine squared of 12 over 3, which is 4. Tappy tap that into the calculator and we get 157.506 gallons per hour. So when we're trying to determine is the tank being emptied or filled, well, it looks like more water is coming in, or water is coming into the tank faster than it's leaving the tank because WT is bigger than R of T. So that means that the tank is being filled. All right, so all we have to look at is that difference between them. If the difference is positive, or just recognizing that in is bigger than out, that's how we know that the tank is being filled. So now the second part of this problem is when is the volume of the water at its maximum? Now, if we had a function for volume, we could go ahead and find the critical points and find the second derivative and use second derivative test. But we don't have a function for volume. We have two functions that deal with the amount of water, or the speed at which that water is coming in and going out. Now, one thing about the functions that we have is they're pretty gnarly, and the AP exam does this to you when you have a calculator active portion, is they give you functions that are kind of too messy to deal with by hand because they want you to use your graphing calculator to handle them. So that's what I'm going to do. So I've got my graphing calculator here. I've typed in my functions for the rate that water's coming in and the rate that water's coming out. I'm almost ready to start solving this problem, but the thing is we want to maximize the volume, and I don't have a volume function. So in order to create that, what I'm going to do is create this function, v of t. Now, this isn't our volume function, but it's going to be the rate of change in the volume function, because the two functions that we have w of t, which is our rate at which water is coming into the tank, and then we have our r of t, which is the rate that it's leaving. So I'm going to subtract what's going out, add what's going in, and subtract what's going out. Now the graph is pretty messy, so in order to clean it up, what I'm going to do is just turn off my w and my r functions so that the only function we're really looking at is this r of t function. I should reduce my window since this is only good from 0 to 24 hours. I'm going to let my window go from 0 up to 24 hours. And so here we have a really good picture of that rate of change in the volume in the tank. Since this function that we have is a rate of change function, it is a first derivative function. So we can, in essence, use a first derivative test in order to find out when is this volume going to be a maximum. So in order for it to be a maximum, we need to see the volume function change from increasing to decreasing, which means that our volume function, or the derivative of our volume function, which is v of t, we want to see that change from positive to negative. So we go ahead and start looking at different points in time. When it's going to change from positive to negative is when that v of t function is 0. So it's going to be right here, right here, right here, and on the ends. Now, when it comes to those endpoints, we only see what's happening on one side, so we don't actually know if it changes from positive to negative or negative to positive. So these two endpoints are non-starters for when the volume could be a maximum. So we look at, first of all, this one that's at about 6. We see that it's to the left of this point. We're going from our volume function being negative to our volume function being positive. That means that at this point, our volume is going to be at a minimum, not a maximum. When we look at the next point in time, at this 13 point something, we see that it changes from positive over to negative. So that means this is where a max is going to happen. And then when we look at our last possibility right here, we see it's to the left of that point, it's negative, and to the right of that point, that rate of change in the volume function is negative, so there is no change, which means our maximum has to happen right here. So where is that point? Well, luckily we're on Desmo, so we just tap it and see that that point in time is going to happen when t is 12.974 hours after midnight. So that means at almost 1 o'clock in the afternoon. Now, one thing about this problem is don't get too freaked out about it, too overwhelmed by it. We're going to look at this type of problem quite a few more times before now in the AP exam, but this is just kind of our first run at it. You'll get your second chance at it when you do your homework today.